talking about a 3D lattice, and I'm drawing a 3D lattice on the board. So for those of you who are not familiar with the EPICQUR lattice, that might have been a little bit difficult to visualize. So this is also obviously 2D, since we're still on a plane, but it's a little bit perhaps better visualization than what I was able to draw. So what you're seeing here is these tetrahedra. So those are the tetrahedra that I was talking about. And then when I draw two tetrahedra neighboring one another, it's basically this unit here. And so you see that you have 1, 2, 3, 4 sites, and then this guy here on the, the up-pointing tetrahedron now becomes, is here hidden a little bit in the back, okay? And this is embedded in a cube. That's just to say that actually the Bravais lattice, in which you can embed, out of which you can build the EPICQUR lattice, is actually cubic. In fact, the EPICQUR lattice is can be built. The underlying Bravais lattice is the FCC lattice. But anyway, the important thing is just this tetrahedron structure. So this is another view of it without colors. So maybe, I don't know if that helps other people who see things differently. And in any case, the materials I was actually talking about, and that perhaps Colin will talk about too, I don't know, tomorrow. So there are materials which have this structure. So yesterday I mentioned this homium instead of R being one of these guys, or that's dysprosium. So the rare earths here are the guys here that it's usually the line that you put at the bottom, but actually it fits right here. Okay, so this is in the lanthanide series. Another thing, since I won't be switching back and forth, okay, so this again, here I'm using to show what the local axes were. So this local z-axis, every time for this part of the lecture, every time I write SZ, it actually means these local z-axes, which I was trying to draw on the board yesterday, and for which some of you may have been confused. And so the x and y axes, they lie in this plane, and there is some choice of them, for which you can write this Hamiltonian in this way, and this is the way that basically has the fewest kind of coefficients here in front. And as I mentioned, this was actually the most general nearest neighbor Hamiltonian that you could write based on symmetries. And so actually all materials which can be described by a nearest neighbor Hamiltonian, that is for which the longer range interactions are very weak, which is the case for rare earth, for example, actually should be described by this Hamiltonian, if there's indeed a good effective spin half. And so any material basically is going to be represented by a point in this three-dimensional phase diagram. It's only three-dimensional and not four-dimensional, because here I've put down, I've written this in terms of the dimensionless constants, normalized by this JZZ term, which is the classical spin ice guy. And so classical spin ice would just be this point here. In fact, it's just a very singular point in this more general phase diagram. This is another picture. Again, maybe it's better than what I drew on the board, which showed you this spin flip here. So these would be all the 6 2-in 2-out states. Again, maybe you can see them a little bit better here. And then this was showing you the spin flip. So here you had the 2-in 2-out configuration for both tetrahedra here. If you flip this spin, what you created here was some defect here, so some 3 out, 1 in this case, and some 3 in, 1 out in this case. And we'll actually define each of these to have some what we'll call charges. So the defects we'll call now charges. And this is what I'll talk about today. So the rewriting of the spin Hamiltonian, which like I did yesterday, except now we will be able, thanks to this a little bit more complicated rewriting, we will be able to include the matter field, so go away from just the lowest excitation, so the lowest the ground state and then the photon modes. We'll be able to include more. Oui.
Just a question. I mean, you mentioned that, I mean, yesterday that there were this emergent photons as excitations
Yes.
in this lattice.
Uh-huh.
Is there a possibility of making, so to say, them visible? What they look
Yeah.
like in spin language?
I'll come to this. They're Gsd correlations. So you could see them in principle in neutron scattering by measuring the SCSZ part of the structure factor.
So I suppose that these are extremely long wavelength.
Yeah, so they're gapless, so k equals 0. But I'll come to this actually because it's important. They actually have a structure. It's the same dispersion relation as phonons, well, with a different velocity, obviously. But the structure factor, the weight is different. So the weight vanishes at k equals 0 and omega equals 0. So this is a little bit out of order, but since I won't be, jumping back and forth with the projector, this is, for example, one way. I mentioned that all the materials could actually be placed on this phase diagram, and this was our first attempt. But then there's been more and updated values, for example, by Radu, of how to actually extract these parameters. So how do you place a point in the phase diagrams? Okay. So how can you tell what these exchange constants with numbers actually are? And one way to do this is actually to polarize the spins in a high field. So for these materials, for rare earths, 5 Tesla is a very high field, where all the spins are polarized along the field, essentially, or all the moments are polarized along the field. And so in that case, the ground state is ordered. You know that if you're going to apply a very large magnetic field, you're going to polarize the spins, okay? And so then you can actually talk about spin waves fluctuating along this polarization direction. And spin waves are sharp, as Colin mentioned yesterday. And so you can actually, since this in principle can be, these experiments, you can extract all these structure factors in 3 dimensions. You actually have a very large space, which provides some good constraints on how to extract these parameters. And so this is from spin wave theory in high field, so setting spin wave theory at 5 Tesla. And so one thing I would like to mention here is, despite the fact that we do spin wave theory and all these approximations, and that we take, for example, in Holstein-Primakov, S1/2 to be large. We say S1/2 is large, at least in the spirits of S1 large, S1/2 large. It actually works well. So all these approximations we do, which may seem unjustified, actually, you can see that that they work beyond what you might expect. And I think that's it. Okay, so now I'll go back to what I was telling you about yesterday, and in particular about this rewriting of the spins beyond perturbation theory. Because yesterday we could only do the low energy manifold because we were doing perturbation theory, and so we had no way to access these defect tetrahedra. So now we'll include them. And so the way to do this is still to rewrite the spin operators, so as the SZ component, as the electric field here. We also may label it as small sz, so that's just the same as before. But what we know here, so the procedure, in order to take into account these defects and actually look at them, because these are the ones we're interested in, is actually we have our Hilbert space, which is our spin Hilbert space. Okay, and we enlarge it fictitiously to include the spins, but also to keep track of the charges here, the charges here being the defect tetrahedra. To remember to write big, I guess. Okay. And then, because this no longer is the actual right Hilbert space to describe our spin space, well, we need to impose the constraint that the charges that we have on each tetrahedron, so the charge here lives in this Hilbert space, and it is an integer number, actually is constrained to be sum over r prime s r prime z. And here you saw yesterday that there were all sorts of conventions that we had to take because of the up and the down tetrahedra, so that creating some problems. And so here we can include, if you want to do it actually very precisely, this is plus or minus 1, depending whether you are on the up or a down tetrahedron. So whether R is actually an up or a down tetrahedron. Okay, and so this just sums over the R's, you know, so from 0, 1, 2, 3. Okay, so it's just sums over all the spins belonging to tetrahedron R. Okay, and so this actually projects you back onto this Hamiltonian, and we know that when we act with S plus, as we saw yesterday, so if say you had a spin down, what you're doing, so if you had a spin down here, and now you acted on it with S plus, what you did was you created a charge here and another charge there, okay? So this was a raising operator for the charge, and it created these two defects. And so these two guys are going to be creation and annihilation operators here of so maybe I should write bigger here. So this is R, the neighboring tetrahedron to this side here, and this is R prime. And so every time you act with a spin, you create two defects on the neighboring tetrahedra, and so these guys take care of this. And the relation we saw, it was like angular momentum yesterday, so there is a commutation relation between R and the phi here, which was this, unless there is a minus sign, which maybe I should check. Yeah. And then we have that phi dagger R is related to this phase phi by e to the I phi R. Okay. And so now the idea of having done this is that we can actually explicitly keep track of these defect tetrahedra, which are the good quasi-particles for our quantum spin liquid, good excited particles for our quantum spin liquid. And then we can kind of forget about the spin degrees of freedom and trade them for what are now these gauge fields here. Okay. So because this is a exact rewriting which projects us back onto the proper Hilbert space, we can actually, as I mentioned briefly yesterday, is exactly just plug this in. So this is a simple exercise. You can plug this back into this guy here. And so, for example, if I take this guy, I'm not going to do all of the terms, but you can just do them yourself. If we take this guy, I'll just do Si plus Sj minus plus Si minus Sj plus. What we actually find, so here I'm going to need 3 tetrahedra. So I'll put one here. Okay. I'll call this guy J. And then this will be tetrahedron R double prime. Okay, centered here. There's no spin here, it's just the center of the tetrahedra. And so what we end up with is phi dagger R S plus R prime, phi R prime, and then phi dagger R prime, S minus R, it's a small s here, S R prime R double prime, phi R double prime, plus Hermitian conjugate. And so this actually here is equal to 1 because we have this relation here and at the same site R. And so what we obtain here is actually that we have phi R dagger, phi R double prime, S R R prime. Now I'm realizing there may be again some sign convention here. Maybe this is actually defined to be R double prime R. And then, yeah, so it's this way. But it doesn't matter because they're bosons, but if you want to write it properly, it's actually this. Okay. And so now it's just this guy times this guy equals 1. Okay? So you end up with this S R double prime R prime. Okay. And so what you're seeing here is that you're seeing that this term is actually hopping a charge from tetrahedron R to tetrahedron R double prime. So it's actually a hop from this tetrahedron here to this other tetrahedron there. Okay? And so if you actually do the same exercise with this guy here, what you obtain is you obtain a nearest neighbor hop from this one to this one, but instead of a small s minus here, you'd have a small sz. And this one actually, because now we have pluses here, it actually corresponds, so this one's correspond to second neighbor hopping. Hop. This is first neighbor hop. And this actually corresponds to spin-on interactions. Because the J plus minus term is actually going to lead to terms which have this form where I'm not plugging in the indices, but you can figure them out yourselves. Some S's here. Okay. So, yeah. Yes. Yeah, so I guess I maybe I not have said the word, but so a spin-on, in our case here, is going to be basically the quantum mechanical version of these defect tetrahedra, and those are the fractional particles that can separate at arbitrary distances. And it's a good name for them in this case because at least when these two guys are 0, Sz is conserved, and so they carry some Sz quantum number, and so they have some spin character. They carry some spin quantum number, which is why these fractional particles, in this case, it's a good name for them to call them spin-ons. In the spin-ice literature, they're also called monopoles because of this mapping to electromagnetism that I discussed. Yeah. So these, I would say these guys are not necessarily, at least this one is, yeah, they're not necessarily that much smaller than this. What I meant to say here is that this is the minimal model, the simplest model that would give you a spin liquid. Why it's second neighbor, I think the idea is just probably, maybe I'm wrong, but probably it's because these guys are actually spin-conserving terms. If you only have these two, so they actually conserve as z. And so I think this probably means that you actually have to hop from a defect from an octatetrahedron to another octatetrahedron, because these two carry the same sign of the charge. So I think this is probably related. The fact that it's second neighbor hopping or not doesn't actually really matter. Yeah, thanks. Okay, so now what we're left with is actually we're left with a, so now in this language, quantum spin ice becomes the theory of hopping spin-ons in the background of fluctuating gauge fields plus possibly interactions between spin-ons. Okay. And here it's when I say it's in the background of fluctuating gauge fields, actually the gauge fields are coupled to the spin-ons here. So it's a fully strongly interacting theory. And so basically you have several options in this case. You can actually do some approximation, or you can do it numerically, or you can do nothing. And so the point of view I'm taking here is to do some approximation, which hopefully will give us at least some information about what will happen. And the approximation that we can make, this is the first kind of approximation you can think about making, is to make mean field theory approximation. And because it's not the standard mean field theory where you start doing mean field from the spin operators, we call it gauge mean field theory. Okay. What I want to point out is if you actually had done a regular mean field theory, so I think it's called Curry-Weiss mean field theory on the spins directly, well, when you do mean field theory, regular Curry-Weiss mean field theory on this kind of SI, Sj Hamiltonian, you replace this by Si mu, Sj nu, plus Si mu, Sj nu, minus Si mu, Sj nu. And because the spins are so fluctuating, and we saw this in the superposition in the first lecture, actually these expectation values are going to be 0 or close to 0. And so if you were to do an approximation right away from the spin model, there is no way you would be able to obtain a quantum spin liquid. You just get 0. And so this is definitely not a good ansatz to get a spin liquid. And this is why it's not possible. However, after this rewriting, which I want to remind you is exact, actually you can't get a quantum spin liquid. And so the mean field approximation that we carry out is that, so we'll forget about the we forget about this last term. So I won't be talking about the spin-on interactions. What this can actually lead to, it can lead to some interesting phases. In particular, it can lead to some Z2 quantum spin liquid when the spin-ons actually condense with one another. But I won't be discussing this. This is in a paper, for example, by Sang-Bin Lee and Leon. Okay. So if I now take just these first three terms, actually what I have is I have terms like this, which are phi dagger S with some indices here, and the mean field ansatz that I'm taking is actually indeed to keep in mind, so we're inspired by what we know happens in classical spin ice, and so we want to keep in mind this picture of spin-ons hopping, so hopping spin-ons, because we know they should be deconfined, so in other words they should be able to move around, and so we write down that the following mean field decoupling So this is an ansatz, which allows us to get an answer, which indeed provides us with a quantum spin liquid, which we expect from perturbation theory should exist. So it's a reasonable ansatz. And actually, there's also been numerics carried out on this model, which actually also confirm the existence of a quantum spin liquid. So making this ansatz, making this approximation, is reasonable. I was just checking. And yeah. Okay. So the details of this you can see in this paper. And there is also an archive. This is sometime in 2011, October 2011, or something like this. Okay. So what do we get in this case? Well, now that these will essentially, in the mean field, have some fixed values, which will need to be determined self-consistently. Indeed, the Hamiltonian of gauge mean field theory will be decomposed into H hopping plus H field, basically. Because here what you see is now you're going to have a single spin operator. And so a single spin operator in the Hamiltonian you can think about as a spin in a magnetic field. Okay. And so the hopping Hamiltonian, don't know that I should really be writing it in detail, but basic. Sorry.
I don't quite understand why now the average value of the spin is not zero.
Well, it's actually not the spin, it's this gauge field here, so it's these small s's. Okay, so the small s's are these guys. Okay, so small s plus is just e to the ia r prime, and the real spin is actually this whole guy. And so you could actually still have this guy be non-zero and the whole thing actually have a zero expectation value.
So you're writing the actual spin as two defects and some gauge field.
Exactly, yeah. This is what I was trying to explain, because every time you flip a spin, you create two defects, and we know that the two defects need to be connected by a gauge field. Okay. And this is a little bit different. Actually, the expectation value of SZ will allow, so small sz is actually exactly big as z, but this will actually allow to have a zero value. Okay. But this here will fix to be 1. And again, this it's fixing the expectation value of a gauge field to have a constant value may be surprising. But very clever people that worked on gauge theories in the 70s have figured out that this could actually be justified. And if I have time in the last lecture, I'll try to say a couple words about it. Otherwise, I'll give you some references which are somewhat readable, where you can get a feel for this. Okay. All right. So the hopping Hamiltonian is just a quadratic Hamiltonian in phi dagger phi. Okay. And then this guy, so I'm getting to, just takes the form of some effective field that's some spin s, and this is the small s again. Okay. And all of these, so this involves also some, expectation values of the spins here. And so does this one. This also involves this kind of expectation values. And so all of this needs to be solved cell-consistently, and this is possible. So again, this is done, for example, in this paper. Okay. But now, if you do a mean field theory, you have to know, so then you solve self-consistently. Okay. Now, what does it mean to solve self-consistently? Because for order, for Curie-Weiss mean field theory, it's quite natural, so maybe you don't say it every time, but actually you need to know what it means for each order parameter to be some value or another value. So for example, you know that for Curie-Weiss mean field theory, typically you have some phase. If the phase has non-zero spin expectation value, then you're in the some either ferromagnet or antiferromagnetic phase. And then if S becomes 0, you're actually, so this could, for example, be temperature over J, some exchange constant, say the Heisenberg constant or something, then you'd actually be in the paramagnetic phase. But you know that what is going to be distinguishing, it's going to be distinguishing the two phases is whether or not you have a spin expectation value, which is 0 or non-zero. So this is really your order parameter. So what is your order parameter in this case? So what tells you whether you are in the quantum spin liquid, this quantum electrodynamics phase, or whether you're actually in an ordered phase? Because the ordered phase should actually exist. The paramagnetic phase should also exist. And so here I'm going to draw a table with these different order parameters. Okay. And what we have is the following. So we have a quantum spin liquid phase, which exists, and I'll discuss this in a second, when phi, so the expectation value here of a single phi, is 0. And this means that the spin-ons are not condensed. I'll try to get back to this in a second. And then we have an antiferromagnetic phase. So this is an ordered phase. In other words, it's a product state. You should remind me when I start writing too small, because I think that's what I've been doing. So this is basically when this is non-zero. There are some other, so it's more of a detail as far as we're concerned with entangled phases. But here there is also the small sz, which is also equal to the big sz, which actually can distinguish between entangled phases, like the quantum spin liquid, and antiferromagnetic and ordered phases. So maybe what I actually should have drawn here is actually, that this would be the entangled phase is like this, and the ordered phase is like this. Okay? And now you can actually distinguish between one sort of entangled phase and another, and that's through this expectation value of Sz in this case, which can actually be 0. In this case, you really are in the quantum spin liquid, which was I was describing before. Or you could be, it could be non-zero, and here we call it a Coulombic ferromagnet. And what it just means, it's a quantum spin liquid, but there is an extra tiny little polarization of the spins. And the ordered phase could either have this be 0, and this would be the antiferromagnetic phase. It's still a little different. Or this be non-zero, and this is actually the ferromagnetic phase. Okay. So what's really important here is whether we're considering, for this lecture, really the important part is whether we have this 0 or this non-zero. And so because our spin-ons, so here they're defined to be bosons, so the spin-ons in this case, spin-ons in our model are bosons, then they can condense. And when does condensation happen? When the condensation happens, actually, when the spin-on dispersion relation, and you could just think about this as regular, bosons, actually hits 0. So the spin-ons, in general, have some dispersion relation, which you can obtain from the mean field theory that you solve here. But in principle, there is a gap here. This would be the energy of the spin-ons. So dispersion relation of the spin-ons, and there are actually 4 bands like this. And there is a gap here, because you know that if this gap becomes 0, then actually all the bosons want to go to the 0 energy state. Okay? And then there is condensation. And so if you have condensation, then this means that you have a proliferation of all these defects. And then it just means that if there's just all proliferated, it doesn't really mean anything to even have spin-ons. So the spin-ons don't exist anymore. And in this case, you're actually in ordered phase. So condensed state actually corresponds to ordered state. Okay. And so this is why when you have a non-zero expectation value of phi, which means that all the bosons are going to this 0 energy state, that's when the gap here, delta, goes to 0, then you're actually in an ordered phase. And when it doesn't, when the spin-ons really exist, okay, here the spin-ons don't exist anymore because they've proliferated everywhere. When the spin-ons really exist as individual particles, which you can identify, then actually you don't have condensation, and in this case, when the spin-ons, fractional particles, are well defined, that you're in a quantum spin liquid. Yes?
I thought you said previously that spin-on is one defect and it has spin 1 half.
That's right. But you're worried about the fact it's a boson and not a fermion, which has spin half? Yeah. Well, this is okay because this is just a construction, so we're not constrained by all the, I don't even remember where it comes from now, the fact. But there's for example, in Strednicky's book, there's a nice explanation why a fermion has spin half, in regular why a fermion has spin half for our universe, but this doesn't actually apply here, so spin-ons can have whatever. It's a, there has to be some, so if you, this is the proof of this relation between spin half and bosons, just applies in some context, which I can't recall right now, but it's not like some fundamental thing that should apply to any theory that you actually write. In fact, you could ask the question, go back and ask, is there anything wrong here with having bosons? And actually there is not, so then it's probably okay. Yeah.
You had your construction with bosons
Yeah.
as your partons. Somebody else might want to do it with fermions.
Yes.
Is there something definitive one can say about a model, whether the excitation would be fermions or bosons?
No, so unless an experiment actually tells you that these particles really are fermions. The reason that why we chose bosons is because, so again, if you have fermions, you can only create a single, so basically you could only have charge 1 here, right? You couldn't have 2 more charges in this state, okay? But here we know, because it's 2 in, 2 out, if you flip a spin, then you get 3 in, 1 out. But you could flip another spin and get 4 in, 2 out, in which case the charge here would be 2. So in this construction, they couldn't be fermions. But it doesn't mean that you can't write down fermions. I guess another point is that in 3 dimensions, the statistics are really better defined for these things in 2 dimensions than they're in 3 dimensions. So that's another point where it probably doesn't really matter, I guess. Yes?
You constructed a spin operator out of those small s operators. So
Yes.
the spin operators have the bosonic commutation relation. Does it follow from that?
Well, so if you write this down and then you compute the commutation relations of spins, you can, work through this exercise, and you actually indeed find as SI mu Sj nu.
I think you didn't understand Colin. Colin was asking, he wasn't questioning that. He was asking, does it mean you can't write them in terms of fermions?
No, it doesn't mean you can't. I mean, in this, so you could write Abrikosov fermions if you wanted, but it would be a different construction where you don't have, they're not rotors anymore. So phi is no longer, so this big phi is no longer this. I don't know. What were you asking about?
Asking whether the commutation relations for the spin operators would somehow constrain you to what the spin-on commutation relation should be, and therefore whether it's boson or fermion. But it sounds like it doesn't constrain you.
No, so you could, the spin can also be written in terms of Abrikosov fermions. So there are many, many ways that you can rewrite the spin operator. So what we'll see later is actually you can even write spin operators in terms of Majorana fermions. So long as you verify these commutation relations and you have constraints, Abrikosov fermions. Then you write the spin as F dagger sigma F, and you have the constraint that F dagger F should be equal to 1. And those are fermions, and if you take them to be fermions, you actually also get
Maybe another little comment would be that, from the previous treatment that Lucille gave and all the intuition from classical spin ice that the spin-ons and the monopoles are kind of
Yeah, the, well, I think, well, I know that actually Patrick Lee and his student tried to do fermions, so basically write a construction like this where fermions lived on tetrahedra. It was extremely complicated. There are lots of problems that come about, that's right, because so this construction, I guess I forgot to mention, it is very special compared to the usual constructions, because indeed the spin the defect tetrahedra, so the fractional particles here, they don't live on the same sites as the spins. And this is a very nice description because, and it also makes it very intuitive, because that also maps to the intuition that you get from classical spin-ice, okay? Where you know what your fractional particles and quantum spin-ice should look like. You have an idea of what they should look like. Whereas this is really much more blindfolded, in the sense that you're just taking a spin and then you're rewriting it. This is allowed by algebra, so you can do it, you're fine. But then what do they mean, really, is a different question. Whereas here we have a physical understanding of what they mean. And so this is kind of what you want to try to do when you, again, there's always a choice, because there are many ways you could rewrite the spin in terms of fractional particles. But what you want to try to do is actually write it in terms of fractional particles that you know are physical. So you could choose anything, but if anything doesn't tell you much physics, then it's just an exercise, right? It's not, yeah. Say that again? Yeah, I mean, you could add further neighbors, but I guess that would. Well, this is already sure, but so then you're asking, if you're asking it in this way, lifting the degeneracy of the classical ice manifold, then you're asking about what the other, say, ordered state adding perturbations would be. And so this is a different problem. You could ask what happens if you add further neighbor interactions. Well, you could plug this in and do another very much more complicated mean field theory and maybe get somewhere, but this seems to describe materials very well, because the nearest neighbors is a good model for rare earth. Okay, tested experimentally. Mm-hmm.
The spin-on construction is very nice, and it really, as you say, matches with the classical spin-ice equation. Now, in the quantum problem, we also going to have these magnetic spin-ons or monopoles, right? Are you going to tell us what they are? Would they also have a nice physical?
So, no. So what you can do, because so if you choose this description, then, what the magnetic monopoles are, or electric monopoles, you can choose whatever. What the dual particles to these are other monopoles, so dual monopoles, which basically correspond to defect configurations of the spins, but which are just very difficult to draw. What you could do is you could define other operators, and so that's done in the Hermeli et al. Paper, where you could just do the dual construction. So they don't do particles, but at least they do it in the low energy manifold with E and B. And you could then have this description in terms of the fluxes now going through hexagons, but of the diamond lattice, so kind of distorted hexagons. So you could have a description of the magnetic monopoles in terms of operators, kind of good operators, but then you would lose the description like this. So you could dualize the picture, however, they wouldn't have a nice description in terms of the tetrahedra. So they exist. What they are is so these spin-ons here, they correspond to, in our case, divergence of E non-zero. And then we have the magnetic monopoles. Magnetic, you choose whether you call them magnetic or It's just dual monopoles. Let's call them dual monopoles. And monopoles, and those are divergence of B non-zero. Yeah.
So, if I understand correctly,
Mm-hmm.
there's this choice that we go this sort of fermion route or boson route, and the difference is the constraint that we impose, right?
No, so there are many ways you can do.
Many ways, but each with its own constraint that's not. Because for example, in this boson construction,
Mm-hmm.
it seems to me that you couldn't have more than 4 of these physically per tetrahedron.
Well, physically, you could actually not have more than 2.
Okay, more than 2 then, for
Mm-hmm.
example. So you're restricted to 2 of these per tetrahedron in the physical subspace. But in the fermion construction, you're restricted to 1 fermion per site. Are these 2 restrictions sort of, I guess what I'm asking about is if the gauge fields are emerging from these constraints,
Mm-hmm.
I'm wondering if these constraints are leading to equivalent descriptions of the gauge fields.
Maybe or maybe not. Yeah.
Okay. 'Cause that seems,
But there is no reason why it should lead to the same description.
okay. Because it seems like if we want to interpret the gauge fields as something physical, if we want to say that maybe these things are real, then it would matter if different approaches led to different constraints and therefore different.
Absolutely. Yeah. So the question is whether this actually described. So the whole point. So you could use this. You could say this is an exercise, and I try to plug this constraint, and plug this rewriting, do mean field theory, and see what I obtain. And you could do it for anything you want. The question is which one actually gives you something which is what you expected in the experiment, something which you think describes the right physics. And so, for example, this seems to be a reasonable one, so this is why we went with that one.
I'd like to make a very brief comment in support of using the bosons. One of the things we found in heavy fermion physics, where we tried to describe the paramagnetic state and the antiferromagnetic state, is that if you want to capture long-range magnetic correlations, which you certainly do have in spin-ions, you need valence bonds which are antisymmetric in location. They're if you like, p-wave bonds. P-wave bonds know that they have an underlying bosonic character, whereas short-range RGB, typically, which people use in fermionic, have a symmetric D-wave or extended S-wave type correlation. And so if we associate long-range correlations with antisymmetric RGB, then we need to use bosons to capture it. And so I think the generic feature is that the nature of the correlations from an R&B perspective, long-range magnetic correlations associated with P-wave R&B bonds, and you can't capture them in the fermions in a simple way. Anyway, that's just a comment.
Okay. Yeah. I don't know what your name is, but.
I have a similar question about that one, about the constraints. Because I'm a little bit concerned about the size of the Hilbert space, since you are in the spin 1/2 now, right?
Sorry?
You are now in the spin 1/2, right?
Well, I started off saying that we had spin halves on our vertices, so.
Then I meant the spin operator works on the Hilbert space of size 2, and then you've got this bosonic operator, so you need to have some constraint of your Hilbert space of that writing, am I right?
Sure, but we never look at indeed, so Z, so here the only constraint that we really are imposing on Q is that it's integer. And in fact, we can't have more than plus or minus 2, but we never look at the, more than Q equals 1. So we're fine. If we want, I can constrain that further, but it's not going to change anything in what we're looking at in the solution that we're getting. Because in any case, we're only looking at this subspace. So. Say that again?
The Q is the same as a click 5.
No. So phi dagger creates, so e to the I curly phi is capital Phi, and capital Phi dagger creates a spin-on, so it creates, it's a raising operator for the charge. So phi dagger is a creation operator for the charge. Yes.
In the context of splitting the spin into these aggregates of fermions,
Mm-hmm.
what would the order state be in that case? Because in the bosonic quantum construction, the order state is when they condense, the bosons condense.
In this bosonic, because there are also Schwinger bosons on site. So in this construction, yes, they're when they condense. Uh-huh.
So if you have aggregates of fermions instead, so what would the order state be?
I don't know, but maybe Chun Chao can answer. Did you do that, Chun Chao? You did fermions, right, on the Parachlor lattice, and you did Abrikosov, or? Yeah, so you can ask Chun Chao. Yes.
Maybe just to comment on that question.
Yeah.
Another reason that bosons are good. It's actually hard to write the ordered state in fermions. You can do it, but it's a multi-step process. To do more than just one thing. You make something like a spin density wave out of the fermions, and do some sort of confinement of the behavior. Kind of complicated. It's not easy to write ordered states.
Thanks.
In the table, the expectation value of phi is non-zero, and this is ordered state. Is this totally a ordered state where spin-spin correlations are infinite, or could it also be solved?
Can you repeat the question?
So when the expectation value for phi is non-zero, this indicates the ordered state. Is it a magnetic ordered state, or could it also be a four-spin correlator that emerges or something?
Yeah, so it's a magnetic ordered state in this case. It could be quadrupolar order if you add this term also. So this is a little bit, this is going to depend also. We actually make an ansatz, a further ansatz actually, to solve this in this mean field theory. It's just again described in this paper. So we actually, in addition to this, in order to solve this, again, this is dictated by what is seen in the experiment. We actually further make the ansatz that Sz, small sz, well, I guess this one doesn't matter, mu, so mu is, 0, 1, 2, 3. So depending on which sublattice you're on, is actually 1/2 sine theta var epsilon mu, where epsilon is this 4D vector, which is 1, 1, minus 1, minus 1. You could also take various permutations of this, and where s, small s, mu minus is 1/2 cosine theta. And so in this case, what we have is that, so for this ansatz, for this case, etc., but you could choose different things. You may get different orders. You could get quadrupolar instead of dipolar order. But for this case, the ferromagnetic state is actually such that it has 2 in, 2 out tetrahedra. Here I'm writing up, down. But it's the same for all states. So it actually creates a ferromagnetic moment because of the geometry. Anyway, it creates a ferromagnetic moment. So the net moment is in one of the 1, 0, 0 directions of the cubic lattice. And the antiferromagnet, I guess, so that would be for sine theta and 0. I guess it just all spins in the same direction. So it would just be all spins along same local direction. So that's basically that's theta non-zero and that's theta equals 0. Anyway, but that's a detail. It's a detail. It's very, very late. So I have two choices. Either I start the Kitaev model already, because you'll need this for Radu's lectures, and I don't think I can cover this in a single lecture on Friday. Or I explain how you get the correlation functions and the how you relate this to experimental signals and correlation functions. Yeah. Yes. They're considered in the sense that they're subsumed into these coefficients. We just don't take the further neighbor interactions. I think as far as all the fits to the model that have been done, no one has ever considered further neighbor interactions for at least the ytterbium systems. Yeah, I mean, it's 4f electrons, so in terms of exchange constants, there's no way that you're going to get second neighbor interactions. And dipolar, you can do the calculation, and I forget now, but they're much smaller at the second order. They're much smaller than the corrections already to here. So what second neighbor interactions would do a priori, I guess, would be to order the system more, maybe, I don't know. But if you already are, they're much smaller, their effect is much smaller than these other terms, then, there's also disorder in the materials, probably much more important than further neighbors. Sure. So, I guess I have to decide.
Maybe take more questions from the students, especially ask if they are lost, if some people are.
So are you lost? I hope you're not too lost, but tell me if you're lost. I can try again. Yes. Oh. But I'm pretty sure the experimentalists would not agree with this, so. But maybe you do Kitaev because you're a Radu student. Okay, so let me just say what the correlation functions correspond to so what you probe with each correlation function. You said you were lost, so who was lost where? Yeah. So what was wrong? Where are you lost? Well, if many people are lost, then it's... So what's a question you have instead of just, I'm lost because, I've talked for almost 3 lectures now, so... What do you not understand?
So how could we just replace the S with these and then it changes everything? How the permutation relations have worked out?
Well, that I'm not going to do. I mean, you just work this out and then you should find that this is fine. Probably you should believe me on this one. So that's just technical, and it's right. Conceptually, why it changes everything, but it's not so much that the rewriting itself changes everything, is that we're trying to get to we're trying to see how a quantum spin liquid, which we know should emerge from numerics, from intuition, etc. So where does it, from the perturbative limit? So how could we model this? It's more that this question. And it turns out that this model, by going through these steps, because you keep track of these particles, actually gives you the right phenomenology.
Then these particles are like charges in the particle lattices, right? The phi's.
Yes, so the phi's, you can call them charges, defects, monopoles, spin-on, partons. All of this mean the same thing. They're these fractional particles that can move away from one another because of this large quantum superposition, underlying quantum superposition.
And the fact that they're always in pairs is implying that the average of phi is 0 for entangled states.
The fact that they're in pairs, so that just comes from the fact that they have to be in pairs because you can only create things locally, and these are non-local. And the fact that this is the right way to describe the fact that they indeed exist as particles is because otherwise they would be condensed. If that were non-zero, then they would be condensed, and then they would just not exist anymore. It doesn't really make sense to talk about them anymore. It was you, maybe? Feel free. I mean, I'm here for this, so yeah.
So you mentioned that in experiment disorder could be important.
Mm-hmm.
Heuristically, what would be the biggest change? What is robust disorder?
So I guess this is something everyone wants to know. It's hard. So I want to mention, I said this in the first lecture, so quantum spin liquids are stable phases of matter. So if you have a little disorder, it shouldn't actually matter because they're stable. So if you have perturbatively small disorder, it shouldn't make a difference, and this whole story should be the same. If you have too much disorder, then all hell breaks loose, and you don't know. However, it turns out that if you only started with this model and included disorder, it could actually generate quantum terms for non-Kramer's system, and you could actually generate a spin liquid out of disorder. So it's not on one axis, actually. But it's much more difficult, at least theoretically and also experimentally, because you have less control over what's there. Yeah.
So maybe something more general about how emergence, how new things emerge. I mean, you mentioned people make these parton constructions with Microsoft or Schwinger boson, whatever, and those are kind of blind, and you get whatever you get. Maybe sometimes they are valid, sometimes they are not valid. And here you are building on the intuition of the classical spin ice.
Yes.
And coming up with a picture with emerging particles and new degrees of freedom. Maybe a little more about why. What's the role? How does? Okay, just as an example, why does phi equal to 0 mean that you are staying within the spin ice subspace? Or phi not equal to 0, you will some intuition like that. How are your phases related to whether your state is within the spin ice manifold or you're getting out of the spin ice manifold? Once you, for example, start condensing these spin-ons, you're not going to live in the spin ice manifold anymore, right?
Well, you can live, this single state lives in the spin ice manifold in the sense that it's ordered along it's just one of them. But
Saying that, the spin-ons and the monopoles are the defects, where you don't have two in, two out.
yes, yes.
When you have them in the system, in the ground state, then the ground state is not in the spin ice.
Yeah, sure.
Can we see that phi equal to 0 means that you're basically in the spin ice manifold?
Well,
Expectation value of phi equal to 0?
do you understand that when phi is non-zero, So do you understand that when the spin-on dispersion relation hits 0, which corresponds to this, because when the spin-on dispersion relation hits 0, then you know that the bosons are all going to condense in this phase, and so indeed leave the spin-ice manifold, will get an ordered state. Do you understand that then you're not in the quantum spin liquid phase? You cannot be in the quantum spin liquid phase. So do you understand this line? What I'm saying is that this actually corresponds to the energy of the spin-ons. So this has some dispersion, which is probably something like delta squared plus k squared, maybe, I don't know, or k fourths. K to some power. Okay? And
This is the, you have these phi objects.
yes,
They have a dispersion because they are mobile.
yeah.
It's actually, if you like, a tight binding model for these phi.
Well, it's not, it's just, it comes out of here. It comes out of the rewriting.
Tight binding model for the phi's gives you dispersion like that.
Yes.
And at some stage, when that hits 0, I agree that the spin-on will condense.
Yes.
Why would that make expectation value of phi non-zero?
That's the definition of a condensate. So here I could have written condensation. Condensate is when the bosons acquire non-zero expectation value. The operator for the bosons acquire non-zero expectation value. So then if they're not like this, so this is actually delta, you know, is a function of j plus minus over jzz, jz plus minus over jzz, j plus minus over jzz, field if you have one, okay? And for the right parameters, you have a phase transition. And in fact, we have a phase diagram which looks like this. This quantum spin liquid, and this is about 0.2. And then something like this, and this is the anti-ferromagnetic phase. This is ferromagnetic, and this is this Coulomb ferromagnet, which I talked about. And this is about 0.3. And so here and here, you're in this entangled region for both here. So here you have phi equals 0, and here you have phi equals non-zero. And they have a life of their own. They can't exist. I mean, if these particles exist and have a life of their own, have a right dispersion relation, then fractional particles can't exist in a non-entangled phase. So if they're not, if they exist, then you have to be in a quantum spin liquid phase. One way you can also see this, but I might get lots of questions about this, but if you have S mu, you know, which you've, well, written like this. And now if these guys have expectation values, you're kind of allowed to write it this way. And so you see that if none of these are 0, then this is non-zero. It's another way to see this. Because if these have acquired, you know, spin expectation values, then you're allowed to decompose them now. This expectation value is just the product of the expectation values, more or less. And so then this is non-zero. So it's ordered. This is from mean field theory. Well, so you can place, for example, a terbium titanate to be somewhere here, maybe far, maybe close, probably kind of far. And in these, it's a ferromagnet. So there are various materials which we've been able to place on this phase diagram, which by the way is valid. I mean, it's valid when you're in the small j plus, this description is only valid close to this point here. I mean, it's mean field theory, so it doesn't need to be perturbatively close, but the description is going to fail, obviously, if you're in a completely different parameter regime, because the whole intuition was based on JZZ large, right? So that intuition fails, then, okay. But for materials which might be close to here, I guess various of them have been placed, and this is okay. So, and again, it's a mean field diagram, so you don't actually expect it to be quantitatively valid. So I think that I know there's been numerics which find this quantum spin liquid just along this axis. And they find a quantum spin liquid here, so the U1Q quantum spin liquid. And I think this is basically, they find it, 0.2 divided by 16 or something. So they find a smaller, which is, reasonable because this is mean field theory, which is, at least a somewhat right order of magnitude.
Maybe since there's not that much time left, maybe you can say a few words about how one might.
Yeah, that's what I was going to say. Yeah. So, so what do these? Gauge fields. The A you can't see because that's a gauge field. So, by definition, almost, it's not a thing you can observe directly. However, spin expectation values you can observe directly, and so you can ask, what would I see, for example, in the neutron scattering experiment, which is kind of one of the best probes for magnetism. And so you've seen from Colin yesterday that basically neutron scattering measured, it was the structure, so neutron scattering. It measures structure factors, which are basically spin-spin correlation functions. So in the frequency and momentum, so inelastic neutron scattering, I guess. I'm still writing too small today, I think. Sorry. No, it's not I anymore because we're in Fourier space. And so we had this thing which was some sum, and there was some stuff here depending on mu and nu. And so this is measured at k and omega. Okay. And so actually, the photon you'd measure. So the photon is a linear mode, okay, which is this dispersion relation, and it's linear. Okay, so that's the dispersion relation. But now this gives you the dispersion. So the structure factor gives you the dispersion relation, because when you have a sharp mode, you actually end up with some delta function. This is proportional to some delta function at some modes. But there is also a weight which depends. So there is an intensity, and that intensity is getting picked up by the structure factor. And actually, so you know that for spin waves, or you may know that for spin waves, so for spin waves, which are gapless, so in a Goldstone mode for regular spin waves in an ordered system, for ferromagnets, say, you actually have the intensity at close to 0 omega, which goes like 1 over omega. So basically, you would get a very, very strong signal here at k equals 0 and omega equals 0 for ferromagnetic spin waves. But the photon, so this was just for spin waves, the photon actually, this photon mode actually goes like omega. And so the weight here, if now I draw a color plot, you may have seen, the weight here is strong, but then it vanishes, and then here it's 0. The weight is 0, you can't see it. Doesn't mean it doesn't exist, right? The dispersion relation still goes to 0, but the intensity in the neutron just vanishes as 1 over omega. And the dispersion relation here goes like this: j plus minus cubed over j, the velocity goes like this, over jzz squared. And really, because it's a low energy theory, really you have to look at it very close to 0 energy where it makes sense. And so actually, despite the fact that this could be seen in a neutron scattering experiment, because this actually, the photon corresponds to the Gsd correlation function, which makes sense because it's EE, right? And EE, should give you the photon mode in a regular electromagnetism. And so where you would see it, actually the weight vanishes. So that makes it really hard to see, despite the fact that this would actually be a smoking gun signature of this quantum spin-ice spin liquid. Now for the other particles, so we have the photon here. And so the derivation, at least a simple derivation, we also have a microscopic derivation, but a simple derivation was given in the last appendix of this PRL I mentioned. So you can do some simple thing. There are lots of details there, so hopefully that should be. I wanted to do it in the lecture, but I won't have time. But you can fairly simply get this weight here, which is just related to the fact that E, is minus gradient V minus the derivative of the A here, and this is omega A. So you get extra factors of omega. So when you compute E, you actually end up with omega squared AA, where this would go like 1 over omega, like this guy. But so then in the end, this just goes like omega. This is basically the reason. It's because of this thing. And now for the spin-ons. So each one of them, we said, had delta Sz equals plus or minus 1/2, essentially. And so in particular, when you do a spin flip, S plus, which couples to the neutron, so this is but the spin of a spin, and this would be the spin of the neutron, right? They couple some way, kind of like this, probably. And so when you measure this kind of the spin-ons, they would come from some correlation, which basically relates to some S plus S minus correlation function, okay, so or Sx, Sx, Sy, Sy, so for example, Sx, Sx, so that in the spin system. But the problem here is you might think, okay, well, since we have a nice dispersion relation for the spin-ons here, I should just measure sharp spin waves like Colin showed yesterday for the spin waves, or what I showed you earlier this morning for in a high magnetic field for the spin waves. However, things work a little differently because I shouldn't have erased this. Oops. Because you actually excite two of them. So the way the scattering experiment works is that you're sending a neutron here, which is momentum k and frequency omega, and then it has some spin. Okay. Oh yeah, sorry. Okay, so spin half, and so say it arrives with the spin up here, and then it hits your sample, okay, and there's a spin here, and they collide, and that creates a spin flip, okay, and so then the neutron leaves here, and it leaves with spin down, so it's left in the system delta z equals 1. Yeah. Okay? Yes. You don't have any magnons because you don't have an ordered state. So actually in the Coulomb ferromagnet you do have magnons because you have a little bit of order, but that's a little bit of a, it's important for the actual experiment, but for the entangled state here it's not. I mean, we can talk about it later. Maybe I probably am out of time already, so yeah. So the problem is that here it's, it leaves this in the system, but actually this is shared between, one of my spin-ons and another one of my spin-ons, which each have, some momentum k1 and some momentum k2. Okay? And they carry each, spin half. And so it's also left in the system. It's also left some momentum k. So if it leaves with momentum k prime and frequency omega prime, it's left in the system k equals minus k prime plus k, I guess, and omega equals minus omega prime plus omega. So that's what's in the system. But this should be shared between the two. So this k here should be shared between the two. And so instead of having a sharp signal, you're going to get contributions, all contributions, such that k1 plus k2 equals k, and omega 1 plus omega 2 equals omega, are going to be able to contribute to the signal. So for example, if I have a spin-on dispersion like this, and I have two of them, right, so I have to take two of them, and now the momentum that's left in the system is, say, here at k. To build k, I could take k here, and like k here, and something like this, and then some energy here. Now I'm having a hard time drawing, but in any case, there are many solutions to this equation, which is very different from regular spin waves, where you would have a single solution. And so actually what you get is a continuum in intensity in k and omega space. And so this is particularly not sharp. And this is going to happen every time you have fractional particles, because again of this non-locality, and so it makes it very difficult to probe quantum spin liquids, to get any sharp signature of quantum spin liquids from neutrons in this continuum. All right, thanks.
Questions?
Just to mention, up to now we've been talking about inelastic neutron scattering.
Mm-hmm.
In fact, you can already have some insight with elastic,
Mm-hmm.
using some ordered structure of known field groups.
Mm-hmm.
1, 1, 1, 1 minus 1, 0, you can
Mm-hmm.
some order and get some values of the G plus plus particle.
Yeah, absolutely. So that's, for example, what I showed earlier. So if you apply a strong magnetic field, and in this case you completely get out, so there's an extra axis here in the phase diagram, which would be magnetic field. And you know that that very large field, you're going to be ordered regardless which which values of J plus minus are, and then you can do you get sharp spin waves, and you can get indeed extract these constants. Yeah.
Then from those constants, you look at the phase diagram to understand if it's spin wave or not.
So once we have these constants in a specific material, we can say our material is here. And then hopefully one day somebody will say our material is here. And then we'll do this.
So with the zero field case, we have the
Well, in the zero field case, if you don't have a sharp signal, you can't extract the constants. You can stare at this, maybe you see something, because that shouldn't be the complete absence of a structure, but it's not going to tell you much. And what you could do is try to see this, but again, that's hard because the weight vanishes here.